Let me start this lecture by continuing the discussion we were having last time. So let me quickly remind you what that was. We were talking about two groups, G and H, and both these groups have 6 elements. And we proved that even though they have the same number of elements, they are not isomorphic as groups. So there is no isomorphism from G to H. Let me remind you what the groups were. G was the group of rotational symmetries of a regular hexagon. So a hexagon we have seen has 12 isometries, 6 rotations and 6 reflections. And if you just focus on the rotations, they themselves form a group of size because it's just powers of one rotation. And so the product of any two rotations again gives you a rotation. So this is a group. And there is the other group, which is the group of isometries of a triangle, which also has 6 elements, which has got, there are 3 reflections and 3 rotations. So we had seen that they were not isometric. Sorry, they're not isomorphic. I had indicated last time that there is another way to see the same thing. Let me just finish off by mentioning what that is. So when you want to show that two groups are not isomorphic, what you have to do is find an algebraic property that one of the groups has, but the other does not. That is actually what we did last time, though we didn't spell it out as such as a strategy, but this is what it is, that whenever you want to show that two groups are not isomorphic, you show that one of them has an algebraic property which the other one doesn't. So here is the other way of looking at it. The other proof that, see, G has this property, the group of rotational symmetries has this property that if I take any two elements of G, the order in which I multiply them doesn't matter. So if X and Y are two elements of G, XY is equal to YX. And this is because X and Y are both powers of the same rotation. And so if you write them out, rho to the power I times rho to the power J, it turns out that this is the same thing as rho to the power J times rho to the power I, because both are equal to rho to the power I plus J. But in H, in the group of isometries of a triangle, we know that this is not the case, that the order in which things are multiplied, it does matter. So the reflections and the rotation, if I take a reflection and a rotation and a non-trivial rotation inside H, I know that the order in which they're multiplied, they're composed, does matter. If I compose them in the other order, I will get a completely different answer. So since these two groups have these different properties, one can use that to prove that there is no isomorphism from G to H. I will not actually write that out explicitly. So we wrote out the proof explicitly last time. This time I will leave it to you as an exercise. Use these two facts to verify, to prove that G and H are not isomorphic. So there is no isomorphism from G to H. Now, a little bit about the terminology here. I'm saying that G and H are not isomorphic if G, there's no isomorphism from G to H, but this is a somewhat asymmetric definition. I should also, why am I not talking about the isomorphism, the possibility of an isomorphism from H to G? Well, it turns out that if I have an isomorphism from G to H, there will also be an isomorphism from H to G. So these are actually equivalent concepts, and this follows from this simple theorem that if G and H are groups and phi is an isomorphism from G to H, then the inverse function phi inverse is also a group isomorphism. And because, see, the thing is that phi inverse exists as a function because phi is a 1-1 correspondence. When I say that it is a group isomorphism, I'm saying that the phi inverse also respects the binary operations. That is all we need to check. We already know that phi inverse is a 1-1 correspondence. So what do we need to check? We need to check that if X and Y are in H, then phi inverse XY is equal to phi inverse X times phi inverse Y. So what we will do is, to check this, we will apply phi to both sides of this equation. So first apply phi to the right hand side. Phi of phi inverse X times phi inverse Y. So here what I'm doing is I'm multiplying the two elements phi inverse X and phi inverse Y and then applying phi to them. Since phi respects the binary operation, I could actually apply phi first and then multiply later. So phi of phi inverse X times phi of phi inverse Y. Phi of phi inverse x is just x, and phi of phi inverse y is xy. So this complicated looking thing, phi of phi inverse x times phi inverse y, this is just xy. So when I apply phi to the right hand side of this equation, the equation that I want to prove, it's not known yet. If I apply phi to the right hand side, I get xy. But if I apply phi to the left hand side, I certainly get xy. So phi of phi inverse xy is also xy. So both the sides of this equation, if I apply phi to them, I get the same element. But so these are potentially two different elements of H of G that I want to show they are the same. These two potentially different elements, if I apply phi to them, I get the same thing. But phi is a perfect matching, right? It's a 1-1 correspondence. So if after applying phi, two elements are becoming the same, then they were the same to begin with. And so phi inverse xy is equal to phi inverse x times phi inverse y, which is exactly what I wanted to prove. So phi inverse also respects the binary operations, and so phi inverse is a group isomorphism. Okay, so this completes the proof. It's a very simple theorem. It's actually too simple to be called a theorem, but I mean, I have written out the proof in detail because it's an example of a simple proof that if you're not used to the notion of proofs, if you're not used to writing proofs, then reading this may help you get used to it. So so I know that some of you may be really worried about writing proofs. Firstly, you'll not have to prove anything very difficult in this course, but you should get used to writing simple proofs, and before you can learn to write them, first you should read a few proofs and get used to the way things are written in a rigorous manner. Okay, now I want to introduce a new concept called subgroups. This is a very simple concept. There are going to be quite a few things I will actually want to say about subgroups, which I will say in later lectures. Today, I just want to introduce the definition and say a couple of small things. So G is a group. A subgroup of G is a subset H of G, which is also a group. Okay, but it should be a group under the same binary operation, star. So such that star gives you a binary operation on H, and this makes H into a group. So there are two things being said here. See, first of all, H is a subset. So if I take two elements of H and I combine them using star, I may not get an element of H again, right? Then in that case, star is not even giving me a binary operation on H. So then there is no possibility of H being a subgroup. Also, even if H happens to be closed under the binary operation, that is, if I take two elements of H, I get another element of H. If this happens to be true, even then there is no guarantee that H is a subgroup, because groups have to satisfy certain extra properties. Like, for example, if I take G to be Z and H to be the collection of positive integers, then addition, which is the group operation of Z, also gives me a binary operation on the set of positive integers, but the set of positive integers is not a group under addition, right? So more needs to be checked. So let's make that precise. More precisely, we can say that a subset H is a subgroup if the following things are true. The identity should be in H. X and Y in H implies X star Y is in H. If X is in H, then X inverse is in H. And I should write one more property. I should say that associativity law holds, but I have not written that. The reason is that I don't need to check that the associativity law holds for elements of H, because it anyway holds for all elements of G, which is a much bigger set. So associativity law comes for free. But these are the three conditions that one needs to check if one wants to verify that a subset is a subgroup. So so this is the thing. We do not need to check the associativity law because it is there for free, and so we don't write it out as an extra condition. So let's look at an example. So this is an example that we have already seen, actually, that if A is a subset of the plane, then I can talk about its group of isometries. And all of these elements are actually sitting inside the group of all permutations of A. There may be permutations which are not actually isometry. So this may be a bigger set. It may be a bigger group. But G is sitting in is a subset of this, and it is closed under taking inverses and under composition. So G is a subgroup of this. This is one of the first situations that we actually explored, and though we had not formally defined what we had not come up with the notion of a subgroup yet at that point. Anyway, so here is a trivial example that if G is a group, then G is a subgroup of itself. So this is a particularly silly example, but it's still something that one has to state, because see, every set is a subset of itself. So G is a subset of itself. It's also a group under the same binary operation. So it's a subgroup. Formally, it's a meaningless statement, but I mean, it's not a very valuable statement, but it's true according to the definitions. So since this is not a very interesting example of subgroups, we have a special name for subgroups that are not this. So any subgroup of G that is not equal to the whole of G is called a proper subgroup of G. This is a terminology that is often, we may often have to state later in the course. Okay, here's something little less trivial, that let G be a group and let X be any element of G. Then I consider the set of all powers of X. So I will write it like this, X with angular bracket. So this is a set. And this is the set of all elements of the form X to the power N, where N is an integer. N could be positive or negative. It could also be 0. So X to the power 0 is just the identity of G. Then there is X, X inverse, X square, X to the power -2, and so on. So all integers, positive or negative, do come up in the exponents. And this is an infinite list. Okay, so this is certainly a subset. I'm claiming that it's a subgroup. So this is something you can check. I'm leaving it to you as an exercise, but it's really easy to check because see, the identity is already there. If I take the product of two powers of X, that is again a power of X. It doesn't matter whether the powers are positive or negative. It's the power of two. The product of two powers is again a power of X. This is something you can write down and convince yourself that this is true. What else? Inverses. So if I take a power of X and I take its inverse, that is also a power of X. So that's already a proof actually that this is a subgroup. We will talk about this kind of subgroup later. Let us move on to another example. That so I want to look at the subgroups of Z with addition. So this is the group of all integers under addition. So let M be any integer. I will define this M times Z to be the set of all integer multiples of M. Okay, so for example, if M is 2, I'm just talking about the set of all even numbers here. Okay, so then I claim that Mz is a subgroup of Z. So this is actually very easy to see. See, any element X of Mz, it is actually written as M. It can be written as M times D, where D is some integer. And so minus X is M times minus D. So, which is again a multiple of M. And so the inverse of X is also in Mz. Now let X and Y be in Mz. I want to show that X plus Y is in Mz. So there exists integers D1 and D2, so that X is equal to M times D1, Y is equal to M times D2. And so X plus Y is M times D1 plus D2. And so X plus Y is also in Mz. So these are simple verifications. The existence of the identity is also simple because 0 is equal to M times 0. So that is also in Mz. So it's very easy to see that Mz is a subgroup. So notice I said that even numbers are a subgroup. Odd numbers are not a subgroup because odd numbers are not multiples of any fixed thing. Right? They're just the things that are not multiples of 2, but they are not all multiples of one fixed integer. Or at least they're not all. So there are certainly multiples of 1, but they're not all the multiples of 1, right? So odd numbers do not fall into this pattern. But okay, the question I want to ask is, we have found a whole family of subgroups of Z. Are there any other subgroups? So this is a question that we will answer later on, but I will just leave it for you to think about it. Okay, so now when I want to check that something is a subgroup, so I've got to check that it has got these 3 properties. So I said that, okay, there are actually 4 properties to check that something is a group, but the 4th one, the associativity, we don't have to check. but still there are three properties to check, which are not, it's not a, so the thing is that usually in practice, some of these properties, out of these three properties, um, at least one, the existence of identity, will be easy to check in any situation. Maybe inverse is maybe slightly harder. It's the being closed under the binary operation, that may be the hardest thing to check in any situation. But what we will do is, so here's we'll cut down our work a little further by showing that it's just enough to do one calculation. So this is a test. It's not going to be a huge improvement on the three things that we have to check, but it does help to make your proofs a little more concise sometimes. So again, this is not a very important theorem, but I'm writing it out as a theorem simply because it's a simple proof and it gives you something to read, a simple proof that you can read and understand, so that you can get used to the idea of proofs. So let H be a group and let H be a non-empty subset of G. Then H is a subgroup of G if and only if the following condition holds, that for any X and Y, the element XY inverse is in H. So you can think of XY inverse as in a certain sense, it is like the ratio of X and Y, right? If X and Y were numbers, XY inverse would be the ratio of X and Y. But of course, these are not numbers, and the order in which they're multiplied, it matters. So maybe you shouldn't call it as the ratio of X and Y, but you can think about it just to get a feel for what this result is saying. So you only have to check this, that for any two X and Y, XY inverse is in H. So it's just one thing to check, but of course it is true. We have to check this for any pair X and Y. So this may not save a lot of labor in when you're this may not actually make proofs simpler. It just makes them a little shorter when you write them. Okay. So let's prove this. So I want to prove the equivalence of two conditions. So I take the first condition and prove that it implies the second one. Then I assume the second one. I prove that it implies the first one. So suppose H is a subgroup. I want to prove that this condition holds, that for any X and Y, XY inverse is again in H. So let X and Y be given elements of H. Then as Y is in H, Y inverse is in H. And so the product of X and Y inverse is in H. So X, because we are assuming that H is a subgroup. And that is exactly what we wanted to prove. So one way the result is very simple. It's the other way that we are interested in, really, that if this condition holds, then H is a subgroup. That's what we want to prove. So let's assume now the condition that for any X and Y, X times Y inverse is in H. Now I want to prove that H is a subgroup. So let's first look at the existence of identity element. Let X be any element of H. So H is non-empty, so I can just pick up some element. Then, well, I only see the condition is that I'm assuming that if I take two elements, X and Y, then X times Y inverse is in H. I'm only picking up one element, but then I can say X, I'm taking the elements X and X. Okay, I'm taking X twice. And so then X times X inverse is in H, but X times X inverse is just one. So the identity element is in H. So we have proved that H contains the identity. Existence of inverse also follows just as easily, that now let X be any element of H. I want to prove the inverse of X is in H. I look at the elements 1 and X. As 1 and X are in H, so is the element 1 times X inverse, so which is X inverse. Now products. Now let X and Y be in H. I want to prove that XY is in H. Well, Y is in H, so Y inverse is in H. So now I apply my assumption to X and Y inverse. So X and Y inverse are in H. So X times Y inverse is in H, but Y inverse is Y. So this is just XY. So XY is in H, and so H is a subgroup. So I'm going through this a little quickly, but there's not really much happening here. If you are having trouble digesting this, just read it slowly, and it should not be this should not be very difficult for you. Okay, so now I actually want to move on and talk about some simple examples of groups and do some hands-on calculations maybe. But before we do that, I just want to define, um, come up with a couple of concepts. So one is this thing called the actually, I'm only going to define one concept and do a small observation about it. Um, there's something called the order of a group. So this is actually just the name for the number of elements of a group. So G is a group, the cardinality of the set G. Cardinality is just another word for number of elements of the set. So this is called the order of G. So why am I giving this another name? Why I'm not just calling it the number of elements of G? Well, every subject has its own terminology, and in group theory, it is traditional to refer to the number of elements of the group as the order of the group. So this is what we will call it. Now, a finite group is a group having finite order. So this is going to be of some interest to us because we will be looking at finite groups as examples. Because since they're finite, then you can, it's a little easier to think about them. This doesn't mean that finite groups are generally easier to study, because the study of finite groups itself is a big project, and I think much of it has been done. I mean, people have discovered a lot about them. Some very hard problems in the area have been solved, but still, they're not easy to. One can't say that a group is easy to understand just because it is finite. But still, there are some things that one can easily say about them. Let's look at them. So G is a finite group. I will come up with one basic property of this. Let X be any element of G, and then I look at the set of all its powers of X. Okay, so I know that this is a subgroup of G. I observed that earlier. I'm not going to really use the subgroup part yet, but just observe that this is actually sitting inside G, and so this also has to be finite. Okay, it looks like it's an infinite collection because X to the power anything, but really this is going to be a finite collection, meaning that there's going to be lots of repetitions simply because all this is sitting inside G. So in particular, if I write it out like this, so let me say that the cardinality of G or the order of G is R. If I write down the sequence 1, x square, so on up to x to the power R, there are R plus 1 elements here, but there are only R elements in G, which means that there is going to be some repetition over here, right? So all of them cannot be distinct. And so for some positive integers, m and n, actually I shouldn't say positive because I'm also using x to the power 0 over here. So maybe I should have really said non-negative integers, m and n, but m is not equal to n. So I could say that m is less than n. I have two integers m and n, so that m is less than n, so that x to the power m is equal to x to the power n, and they're both less than r. Okay, so then x to the power n minus m, I can just cancel out the x to the power m, and I'm left with x to the power n minus m is equal to 1. Also, since n is less than or equal to r, n minus m is also less than or equal to r, because m can be as low as 0, right? But it can't be negative. So n less than or equal to r implies n minus m is less than or equal to r. So what have I proved? That there is some integer which is less than or equal to r, such that x to the power that is equal to identity. So this is the result, that let G be a finite group, then for any element x of G, there exists a positive integer d which is less than or equal to the order of the group, such that x to the power d is equal to 1. We will be talking about this a little more detail later on, but for now, let's just go with this. All we are saying is that whatever is the cardinality of G, there is an integer which is less than or equal to that, such that x to the power that integer is equal to identity. This number d will depend on the integer x, on the element x, right? I'm not saying that there is some d such that for any element of G, if I take this power, then this will be equal to 1. Well, that is also true, but we'll come back to that later. All I'm saying here is that for one particular element x, there is an element d which depends on that element, which such that x to the power d is equal to 1. Okay, so that's all we are saying for now. Okay. So now this is where we are going to start doing some calculations for the rest of this lecture. They're sort of very tedious calculations, but it's worth doing. See, I want to understand all groups of order n, where n is a positive integer. This is in general a very hard problem. But what we will do is we will just solve this for small values of n. We'll just do this for n equal to 1, 2, 3, 4. Okay, this much is certainly very easily doable. Next time we'll look at 5, 6, maybe a couple more like that, until we notice a pattern. So we are doing these calculations to notice a pattern. So let's start with n equal to 1. This is very easy. There's only one group. Okay, one thing I should say, when I say list all groups, I mean list them up to isomorphism, meaning that I don't really want to list. See, we have seen that there are groups which may look different, but they're really the same. So then I don't want to put them all in the list, right? I just take two. If two groups are isomorphic, I will treat them as being the same, and I will only add one of them to the list. So when I say that I want to list all groups, I'm just saying list all of them. That is, come up with a list such that any group of that size, of size n, is isomorphic to one of the groups in the list. Okay, so that is what I want to do. So when I'm talking about n equal to 1, groups of size 1, there is only one group essentially. Okay, up to isomorphism, there is only one group. So there is just the identity element. 1 times 1 is 1. This is the group, right? Nothing more to it. N equal to 2 is very easy also. Well, let G be a group of order 2. Then G contains 1 and it also contains some other element X. So this is an element X which is not equal to 1. So, well, how do you multiply? So this is now our complete list, right? 1 and X, these are all the elements. How do you multiply them? 1 times 1 is 1. X times 1 is equal to 1 times X is equal to X. So the only mystery is what is X square? Well, what can X square be? It can either be 1 or it can be equal to X. If X square is equal to X, then we can cancel out X, right? Because we know that we can cancel out the same element from both sides of an equation for groups, as long as it's on the same side of the expression. Anyway, so here X square equal to X, you can cancel out X and you get X equal to 1. But that is not true, right? Because we assume that X is something different from 1. So this is actually not possible. So X square equal to X is not possible. This is actually a contradiction. So X square is not equal to X. So then X square has to be equal to 1. That's it. That is all you can have. And so then you get this, you write down this complete multiplication table. There are no other choices that you can have. And you can actually verify. See, just because I have been able to write down a complete multiplication table doesn't mean that I actually have a group. I have to still check that associativity holds and all the other properties are holding. So does everything have an inverse? Yes. Does associativity hold? Well, yes, you can check that it does. Anyway, this is a group that we have seen earlier. You will have seen, we have seen a multiplication table like this earlier. Anyway, moving on. So n equal to 2, there is only one group of order 2. N equal to 3. Well, suppose G is a group of order 3. Well, let us just list the elements. So this is my list, 1, X and Y. So basically I'm assuming that X is not equal to 1, Y is not equal to 1, X is not equal to Y. These are all 3 distinct elements, right? Certainly, see, when I say order 3, 1 is anyway there, that I know. The other 2, I'm just giving them names, X and Y. So then what is X square? Well, again, by the same argument as before, X square equal to X is not possible, because then I can just cancel out X and then I'll get the equation X equal to 1, which I cannot have, right? Because by assumption, X is not equal to 1. So what can I have? Well, I either have X square equal to 1 or X cube equal to 1, right? Because that has to happen. Either I get X square equal to some power of X, which is less than or equal to 3 is equal to 1. So either X cube square is equal to 1 or X cube is equal to 1. Suppose X square is equal to 1. This is the case that we are going to deal with first. So 1 comma X squared, I should have written 1 comma X. This is 1 comma X is a subgroup of G. I will not really use this fact that it's a subgroup. It's just, I just know that it is the case because these are all the powers of X now, 1 and X. X square is again 1. So then I will list my elements like this. I will write 1x and I will write y below this. So why am I writing y below this like this? Why am I not writing it to the side here? Well, it's just to lead you towards a pattern which will maybe become clearer in the next lecture. But for now, let's just go with this, that I've written these two elements like this and I write y below. Well, what is yx? Right? I've got all my three elements. What is yx? Well, what could it be? It could be either 1, it could be x, or it could be y. If yx is equal to 1, then what can I see? I see that y is equal to x inverse. But x square is equal to 1. So that means that x is actually its own inverse. So x inverse is also equal to x. So if y is the inverse of x and x is also the inverse of x, we have seen that inverses are unique. And so x is equal to y. Well, I mean, actually, I don't need to refer to that here. Just these two equations, y is equal to x inverse and x inverse is equal to x. This gives me x equal to y, but that's not true, right? We have assumed that 1, x and y are distinct. So this is actually a contradiction. And so yx cannot be equal to 1. So if it is not equal to 1, what can it be? It can be equal to x. But then if yx is equal to x, I can cancel out x and I get y equal to 1, which is also not true because I assume that y is different from 1. Again, I have a contradiction. So yx is not equal to x, but then yx has to be equal to y. But then I can cancel out y, and then I'm left with x equal to 1, which is also not true because I have assumed that x is not equal to 1. So this means that yx actually cannot be defined at all. It's not equal to 1, it's not equal to x, it's not equal to y. So that it cannot be equal to anything, which is a problem, which just means that there is no such group, right? All this started because we assumed that suppose x square equal to 1. So this is where all the possibilities ran out after this, because we couldn't define yx to be anything. And so x square cannot be equal to 1. Okay. So x is not equal to 1, x square is not equal to 1, and so x cube has to be equal to 1. Actually, I could have just stopped over there, but what I will say instead is that x square, it could be, yeah, I could have just said that, and actually it would give me a shorter proof of what I'm about to say. But okay, this is still fine. See, what I have proved is that x square is not equal to 1. I also know that x square is not equal to x, right? So yeah, so x square is not equal to x square is not equal to 1, then x square has to be equal to y. So then my list becomes 1x x squared. Instead of writing y, I can just write x squared. But then what is x times x squared? X times x squared is, well, actually now I'm giving you, since I didn't use the fact that this result I had proved earlier, I'm having to write a little more. X times x squared is not x, right? Because that will give me x squared equal to 1, which is a contradiction. I also cannot have x times x squared is equal to x squared because then I could cancel out x squared and I will get x equal to 1. So x times x squared is equal to 1. So x cube is equal to 1. Yeah, so this I didn't really have to write a long proof like this because I have already proved this. But anyway, so the point is that now I can just write out my multiplication table very easily. It's just powers of x. And the idea is that they only go up to 2. After 2, I come back to 1. 1x x squared and back to 1. So if you notice, this is really just the group of rotational symmetries of a triangle, of an equilateral triangle. Because there were only 3 rotations. And if I take the rotation through 2 pi by 3 and call it rho, then rho cube was 1. So this is just the collection of rotational symmetries of an equilateral triangle. This is the only group up to isomorphism. There are no other groups of order 3. Any other group of order 3 basically just looks like this with some relabeling. Okay, now what about n equal to 4? Now let x be an element of G such that x is not equal to 1. And let us list out the powers of x, 1x, x squared, and so on. Well, I know that there is some d less than or equal to 4 such that x to the power d is equal to 1. So among these powers, 1x, x squared, x cubed, x to the power 4, one of them has to be equal to 1. But I already am assuming that x is not equal, sorry, 1 is among the four powers, x squared, x cubed, and x to the power 4, one of them has to be equal to 1. I know already that x is not equal to 1. That is my assumption. So x squared equal to 1, x cube equal to 1, or x to the power 4 equal to 1. I will handle these possibilities one by one. Suppose x squared is equal to 1. Then I will write out my list like this: 1, x, y, and z. Okay, so what is yx? Again, the same question as before. Well, we have already seen that yx cannot be equal to 1, it cannot be equal to x, it cannot be equal to y. See, earlier when I was talking about groups of order 3, my problem was that when it came to finding out what is yx in this situation, x square equal to 1, I ran out of elements. But now I have a third element, which is z. So I can just say yx cannot be equal to 1, x, or y. So then it has to be equal to z. So let's say that yx equal to z. And so my list actually looks like this: 1, x, y, and yx. So now you already see a little bit of pattern. What I've done is I've put things in a row, and I've multiplied that row by y. And that's how I created my second row. I'm doing this for a reason. You will see the reason later, much later. Anyway, so now I have got this, my 4 elements listed like this. Let's talk about other products. What is y squared? Again, y squared is not equal to y because y is not equal to 1. If y squared is equal to yx, then I will cancel out y and I'll get y equal to x, which is again not true. So we have two cases: either y squared is equal to x or y squared is equal to 1. And I will explore these cases separately. So let's first look at the case y squared is equal to x. So if y squared is equal to x, in this list, I have got 1, y, this is y squared, and then y times y squared. So this is y cubed. So basically, I just have all the powers of y. 1, y squared, and y cubed. And then what is y4? And they are all distinct. That is one thing. So then y to the power 4 has to be equal to 1 if I just apply my result earlier. But again, I have proved this in this long-winded way that y to the power 4 is, what is it going to be? It's going to be one of these 4 elements, right? Because that's all that is there. If I just go through these 3, I will run into contradictions, and then y to the power 4 has to be equal to 1. So again, as I said, this is, a long-winded way of doing this. I didn't have to. See, y, I already know that some power of y between, y squared, y cubed, y to the power 4, this has to be, one of these 4 things has to be identity by my earlier theorem. And if I, so if I just go, at least I mean, okay, maybe all these calculations one has to do. Okay, fine. So y to the power 4 is equal to 1. No, so one of these powers, the shorter argument is that one of these 4 powers, y squared, y cubed, and y to the power 4 has to be equal to identity. And I'm already assuming that y squared, and y cubed are distinct from 1. So y to the power 4 has to be equal to 1. That I already know. But if you don't see that, okay, here is a longer argument. Okay. So in this case, the group is again something understood, right? This is this group of rotational symmetries of the square. Just powers of the same thing, with the idea that after you go beyond y cubed, you come back to 1. There's only a certain way these things can, I mean, you have to verify that associativity is holding, etc., etc. All that is fine. Actually, that works out fine. We will give these things a name later, but right now you can just recognize it as the group of rotational symmetries of the square. This is one possibility. Okay. So the other possibility is, so I mean, we are actually going through different cases here. So right now we have already, we are assuming that x square is equal to 1. In that, there is a sub case that either y square equal to x or y square equal to 1. So now we are looking at this situation where x square is equal to 1. So we are also working with, y square is equal to 1 and x square is equal to 1. So then my list looks like this: 1, x, y, and yx. What is xy? Well, xy has to be one of these 4 things. If xy is equal to 1, then y is equal to x inverse, but x square is already equal to 1, so x is equal to x inverse, so x is equal to y, which is a contradiction. So xy cannot be equal to 1. So why am I calculating xy, by the way? Because I've got these four elements. I know how to multiply y and x in a particular order, right? Y times x is yx. So it's natural to ask what is xy. We have seen such calculations earlier. So xy is not equal to 1, then can it be, what else can it be? Can it be equal to x? Well, if xy is equal to x, then you can cancel out x and you get y equal to 1, which is a contradiction. If xy equal to y, then you can cancel out y, you get x equal to 1, which is a contradiction. And so xy has to be equal to yx. So which just means that when x and y are multiplied, the order doesn't matter. And now we can calculate all the products very easily, and we can fill out the multiplication table. So I've just done an example that suppose I want to calculate xy times xy. Well, rearrange the brackets so that the brackets are now around the middle yx. Then flip that around using this equation, yx is equal to xy. So replace this yx by xy, and so I have x times xy times y, which is x square times y square, which is equal to 1. So the square of xy is also 1. And so I have got this 1 on the diagonal, right? I only have 1s on the diagonal. And this is, you can check. I mean, of course, I'm not checking this associativity, holding, etc. All these things have to be checked. We will actually recognize this group as something much simpler later on. For now, you can just check that if you feel like it, that associativity is holding. It might actually be good for you to check, to do this calculation yourself and fill out this table on your own. Anyway, so this is one possibility of a group. This is certainly a group. So we have found two groups, right? We have found this group and we have found this group. So this actually takes care of the case x square is equal to 1. Right? All this calculation was happening under the case x square equal to 1. So now suppose x square is not equal to 1. X is not equal to 1, x square is not equal to 1. Then you have to look at x cube equal to 1 and x to the power 4 equal to 1. These are the things that we have to check. Now we are done with the case x square equal to 1. Yeah, this should have been a not equal to sign. What if x square is not equal to 1, but x cube equal to 1? Then my list looks like this: 1, x squared, and then I write y down here. Again, I'm trying to write things in a certain pattern. I ask the familiar question, what is y times x? Right? These are all my elements. These are the 4 elements. What is y times x? Again, you run into a problem. You will find that you will not be able to define y times x as any of these 4 elements. If yx is equal to 1, I will run into a problem. I will end up with y equal to x inverse. But x inverse is actually x squared, right? Because x cube is equal to 1. So x times x squared is equal to 1. So x inverse is actually x squared. So then y is equal to x squared, which is a contradiction because I'm assuming that y is different from x squared. If yx is equal to x, I can cancel out x and I get y equal to 1. If yx is equal to x squared, then I can cancel out x to get y equal to x. So yx cannot be defined at all, actually, right? Well, actually, I should have written yx equal to y, but that also leads to a contradiction. If what is the contradiction? If yx equal to y, I can cancel out y to get x equal to 1. And so yx cannot be defined. And so x cube equal to 1 is not possible. Okay, so we don't need to worry about this. So now we are left with the final case. X squared is not equal to 1, x cube is not equal to 1, and so x to the power 4 is equal to 1. So then my list is 1x, x squared, x cubed. So these are all powers of x, and then x to the power 4 is equal to 1. So this is actually looking very much similar to what we already have, this situation of powers of y. Here it's just different. Now you have all 4 powers of, these powers of x. So this is going to behave the same way. And so we are now, if you just write this out, you'll get the group that is isomorphic to the one that we already have. So we will not write it again. So we now see that we only have 2 groups of order 4, either this one or this one. These are the only 2 isomorphism classes of groups of order 4. So yeah, so this is a very, this looks very tedious, but one thing is that we are laying things down in a pattern which we will recognize later. But also, if you don't have to remember these calculations, but go through them and make sure that you understand them. Okay, because this will help you feel more comfortable with groups. Okay, so next thing is we will next time we will look at groups of order 5 and 6, and maybe then we will stop and then we will nail the pattern that we have been trying to build up to.